Hi, this is Team 7's presentation for problem 1. We're going to be looking into designing a supply chain. So for this problem, we're looking at the company Van Horn and evaluating its manufacturing and logistics strategy. We want to make sure it's operating as efficiently as possible. Some moving parts of this company: it has retail customers, it has plants that it produces at, and warehouses that it's stocking. For part 1, we want to minimize the monthly operating costs of the supply chain, and for part 2, we're looking for which plants and warehouses are operational in order to meet demand as effectively as possible. Since for part 1, we're already minimizing for like the lowest cost, the solution to part 2 should come from that. For the setup, we have a few inputs. First, the plants that produce the ACs, which are the supply node, warehouses to store the ACs, which are the transshipment node, and customers to buy the ACs, which are the demand node. There's a lot of going into this product for the input, and it'll be more clear when we're at the spreadsheet. For decision variables, we're looking at the units that need to be produced and shipped from each combination of plants and warehouses. And one important thing is each plant has an activation variable, so it's a binary 1 or 0 whether the plant is active or not. The second decision variable are the units to be shipped from each warehouse to each customer in order to meet the demand. Again, warehouses also have an activation variable. Moving on to constraints, we are limited by the plant's capacity and activation, the warehouse stock and activation, and the customer demands. The objective is to minimize the monthly operating costs for the supply chain. And this will help us solve both parts 1 and parts 2 of the problem. So the solutions for part 1, we want to look at the minimum monthly operating cost, which is $855,000. So moving to the spreadsheet, at the top we have the input variables, which are the costs of producing and shipping to warehouses, and again the costs of shipping from warehouses to customers. We also have the fixed costs to keep the warehouses and plants operational, as well as the plant capacity. In addition, we have the customer demands as well. Moving on to the decision variables, we have plant 1, the table 1 and table 2. Table 1 looks at the units that must be produced and shipped, and table 2 looks at the units that need to be shipped from the warehouse to the customers. Again, these need to be integers because they're products and we don't want to be cutting products in half to ship them or anything. And then importantly, there's also the activation variables, which tell if the plant is active or not. One thing I want to mention are also some of these other variables. We have the total warehouse stock, which is the sum of everything in the warehouse, as well as these fixed costs. These are important because we only have to pay these fixed costs if a plant is operational, which is decided by the activation variables. Then moving on to some of the constraints, we have plant capacity. We want our production volume to be less than the plant capacity. We have the total warehouse stock. We want our shipping volume to equal how much we have in stock. And finally, demand. We want to make sure that our customers' demands are being covered. One important thing I want to mention about the plant capacity and warehouse stock, our inputs such as the plant capacity and total warehouse stock are multiplied by the activation variable. This allows us to only keep the information for plants or warehouses that are activated. And when we optimize, see, this is already optimized, but I'm going to be moving to a screen so we can show it actually being optimized. So we have random variables, and then we're going to see it optimized. And as you see, the solution is 855,000. So for part 2, we're looking at which plants and warehouses should be operational to keep the cost most effective. The answer we get is plants 2, 3, 5, and 6, and warehouses 3 and 4. We can easily see this in the spreadsheet by the activation variables. Only 2, 3, 5, and 6 are activated, and warehouses 3 and 4 are activated. This is also shown by the plant capacity. Those that are not being used have 0 because they're not activated. So one really important thing for this project are the variations. We looked at two variations, no constraints in the supply chain and few constraints in the supply chain. So for no constraints, we wanted to bring the plant capacity to 11,000. This way, in case like a plant could produce all of them, all the units, it can. And that's actually what we see when we optimize. Right now, this is not optimized, but once we optimize, we see that one plant does produce all of them. It's plant 5 produces all of them, and warehouse 3 keeps all of them. And then let's look at the fewer constraints. Here we sent the plant capacity all the way to 500. And right now we're not optimized. But when we optimize, we see that once again, the solver chooses as many units as possible from plant 5, then plant 4, then plant 2. Overall, this shows that the optimal solution involves activating as few plants as possible in order to reduce the fixed costs that we talked about before. Um, so all the things that we saw here are variations of the original problem, which allow us to see different patterns that we weren't originally able to see. So this was all really interesting. So thank you for looking at our presentation. Stay safe.